All right, we're back. All right, so here's what we're going to do. Let's open up the third chapter 3 appendix. We'll just quickly review what we were doing yesterday, and then we'll look at the new material. We might have time to take a peek at chapter 4. We'll see how that goes. Chapter 4 isn't posted just yet because I'm still working on it, but we can still start it at least if we have time tonight. If not, we'll take care of it on Thursday. So anyway, just a quick review. We were looking at how to take derivatives for the inverse trig functions. And just a quick reminder, what exactly is an inverse trig function? Let's go back here real fast. Essentially what you're doing here is you're saying if the sine of theta is, let's say, 0.5, the sine of 30 degrees is 0.5, the arc sine of 0.5 would therefore be 30 degrees. In other words, you're taking the same idea, but you're working it backwards. You're saying what angle corresponds to a sine of 0.5. Okay, so that's what it really means. So it's sometimes called an inverse trig function, arc sine, which sometimes is written as sine with a little -1. But the book points out that that can be very confusing because that seems to imply that the arc sine is simply 1 over the sine, and that's clearly not the case. So just remember, these inverse trig functions essentially reverse the process that we take when we calculate a sine or a cosine or a tangent. We're here, what they're doing is saying the sine of theta is calculated as the opposite over the hypotenuse. The arc sine means that we're taking the ratio and turning it into an angle. And then, of course, there are formulas, standard formulas for calculating the derivatives of these inverse trig functions. And nobody expects you to memorize them. The chart is right here. But I do want to point out that if we are taking the function, let's say the arc sine of not x, but some function of x, g of x, then the formula has to be, is a little bit more complicated because we now need to apply the chain rule, which means that we end up, in this case, with 1 over 1 minus g of x squared instead of x squared. And then we have to multiply that result by g prime of x. So every time we use the chain rule, what effectively happens is you're applying the rule in such a way that you end up with some result times the derivative of the original function. So we'll see the chain rule all the time in this course. It shows up everywhere for functions of any reasonable level of complexity. The chain rule is often going on behind the scenes. So here we have for these, just remember, this is just for x itself. As soon as we get to a more complicated function, we have to replace that with the chain rule. Like here, this is just a straight ahead application of what's on the table. All you have to do here is look up the derivative of the arc cosecant from this table to get your result. And then you're done. And that's literally all you have to do. But for something even slightly more complicated, like the arctangent of x squared, now all of a sudden we are in fact dealing with the chain rule because x squared is a function of x. And so we need to take into account it's the derivative of x squared. Okay, so how does that work? Well, down here at the bottom, you can see that the derivative of the arctangent of g of x is 1 over g of x squared. And if you notice, I reproduced up here, and I just noticed now that I left off something important. Yeah, so in other words, here we've got x squared. That is being replaced with g of x squared. And then what's missing up here is this g prime of x. Now, the reason why it's missing is because it's actually there, but it's equal to 1. In other words, if you took the derivative here, you just end up with a 1. So we don't really need it. But down here, we do need to explicitly mention that all of this is multiplied by g prime of x. Okay, so we did a few of these. Like in this case, for example, the arctangent of x squared, when you apply the formula, just remembering from this chart that we need 1 over 1 plus g of x squared times g prime of x, and assuming that that x squared is the g of x, what we're going to wind up with here is 1 over 1 plus x squared squared. So remember, this is our g of x, it has to be squared. And then this is g prime of x. Okay, so if g of x is x squared, that implies that g prime of x is 2x. So when we plug all that in, our final result is 2x over 1 plus x to the fourth power. All right, so that was our discussion about calculating the derivatives of the inverse tangent functions. Actually, I'm not sure if we did this one. Let's just take a quick look at it. The arc cosine of 3x squared plus 2x. What is the derivative? So once again, let's go back to our table. And let me just quickly pencil this in here. If we're dealing with just plain old arc cosine of x, the derivative would have been -1 over radical 1 plus x squared. So here, what has to happen is this is now g of x squared. And then we need this g prime of x. Okay, so this one isn't too hard because g of x is a polynomial. And you can see that g prime of x, based on the power rule, is 6x plus 2. And so that will end up going here. So we end up needing just to have -1 over the square root of 1 minus g of x squared times g prime of x. So here, I guess what I should have done, I think I consolidated this into 2 steps. It's -1 radical 1 minus, here's g of x squared. And then you multiply it by g prime of x. What's going on here is that then I've just multiplied the numerator by 6x plus 2. So it just looks nicer like this. But this is fine too, what we have down here. This is what happens when you actually apply the rule. But, often you'll see in textbooks, they will consolidate these answers into something that looks a little nicer. So that's why this is our final answer. All right. Now, here's one. This was an interesting one because this one involves the product rule. It involves an arc sine, but it also involves the product rule. So as always, if we can rewrite this as a product of two functions of x, this would become g of x. This becomes h of x, and the product rule is right here. You may have it memorized by now after using it so many times. What we need then is to figure out g prime of x, which is 2x, h prime of x. And for that, we can go back to our chart because it is just plain the arc sine of x. So it's 1 over radical 1 minus x squared. And now we just plug in the numbers that we have, okay, into this formula down here. So g of x, this will be x squared. This will be the radical 1 over radical 1 minus x squared. Here for h of x, we have the arc sine. And g prime of x is just 2x. And so, as is often the case, I mean, we can leave it like that, or we can just simply clean it up a little. Usually the standard practice is to put in any kind of an expression, the trig functions tend to come last. So you notice how there's the arc sine of x times 2x. And of course, we could have also moved the x squared here, but it's not that important. So the 2x got moved over here, but this is our answer. All right, now this next section is pretty interesting, but it's kind of challenging. Everything we've done up to this point, all the derivatives that we've taken up to this point, let me just add something here. All of the derivatives that have been encountered so far are known as explicit derivatives. We don't usually use that word because it's understood, but explicit derivatives because y is a function of x. Or it has been up to this point. So in other words, what other possibility is there? In other words, if we don't have y written as a function of x, what does that mean? Well, sometimes what happens is a function is so messy that it's not possible to actually rewrite it as y equals a function of x. So for example, let's take a look at this one. Suppose you're told that y is equal to the cosine of x times y. How would you rearrange that algebraically and rewrite it as a function of y equals a function of x? The answer is you can't. So what do we do now? How do we calculate the derivative of this function if it can't be expressed as an explicit function of x? We return to something called implicit differentiation. We're effectively doing the same thing. It's sort of a workaround. We're sort of using the implied relationships between these variables to come up with our result. So the rules are not different, but we have to be a little bit careful when we use this technique. So basically what you're going to try to do is take the derivative of both sides of an equation and then use algebra to factor out dy dx from both sides so that all the dy dx terms are on one side and everything else is on the other side. As long as we can do that, we can still calculate a derivative. Okay, we don't have to have y on one side and x on the other with this approach, but we do have to at least have dy dx all on one side and all the rest on the other side. Okay, so anyway, so let's take a look at an example. Now, this is obviously you recognize this is the equation of a circle with radius 5. And the thing is, I guess in principle, we could have rewritten it as y is a function of x, but let's say that we can use that as a double check. In other words, certainly you could have changed this to something like this. But just to get some practice with the technique, let's just use the different implicit differentiation approach. So what we're trying to find is dy dx. And so here's what we're going to do. First, let's take the derivative of both sides. And of course, always remember dy dx and f prime of x mean the same thing. This is one of Leibniz's. That's one of his ideas. He liked this approach. Newton, I believe, just stuck with the f prime of x. But sometimes each approach, each type of notation has its own uses. It's not the case that one of them is clearly better than the other. It's just that sometimes one of them makes more sense than the other. So we'll use the one that works for that particular problem. So we'll differentiate both sides of the equation. And of course, doing that is no different than, let's say, multiplying both sides by the same constant or dividing. Anytime you take an equation of any kind, if you apply the same operation to both sides, you have not changed the value of the equation. So we can differentiate both sides with respect to x. Now, this is where it gets interesting. Obviously, this is going to be equal to 0. This can be rewritten as the sum of these two. Okay, so let's do that. So we've got, okay. So here what I've done is I've just taken this left-hand side and set it equal to 0. And again, this will eventually lead us to this approach. But what I'm doing here is I'm actually evaluating them each separately. Now, this one is very straightforward. It's clearly just 2x. Okay, and again, just as far as notation is concerned, it's no different than saying this. But it's often easier with implicit differentiation to use the dy dx approach. All right, but what about that y? Oh boy, now we're opening up a can of worms, because it might not seem like it, and I'll show you why in a second. As far as the y squared is concerned, when we apply the differentials to y squared, instead of just getting 2y, we end up with 2y times dy dx. That is the bizarre part that you don't see with explicit differentiation. Right here. Oh my God. So what we're going to do now is see why this is happening. Okay, so first things first. Just as a quick review, we did this a while back. God, it might have even been yesterday. I don't remember anymore, but this is the approach that we can take when we're applying the chain rule. And again, this is coming from Gottlieb Friedrich Leibniz, this approach. Newton had a different way of going about it, but what we can do is rewrite dy dx as dy du and du dx. Now, this is not the only way of expressing this relationship. What we're going to see here is that we're going to assume that this u is a function of y, and y is a function of x. So therefore, u is the composite function in this case. U is a composite function f of g of x. So that being the case, we can rewrite this a little more conveniently as du dx equals du dy dx. So, I mean, realistically, it's the same thing. We just changed the letter slightly. So what do we do now? And by the way, you can tell this works because these clearly cancel out. So anyway, how does this help us? All right, so remember, what do we have here? We're saying that the derivative of y squared with respect to x is 2y dy dx. And the question is why? Okay, here we go. So we'll start by defining u as remember we said here that u is a function of y. So let us define it as y squared. Okay, now of course, remember, we're trying to figure out the derivative of y squared. So let's let u be y squared. Now, we don't have to specify here. Y in principle can be any function of x. So applying this technique, what do we know? Okay, well, again, we have du dy dx. Because of this relationship, what you're basically doing is taking the derivative of u with respect to y, and that part gives us 2y. And that's what goes here. But then we still have dy dx. Now, if we don't know what y's function is, we can just leave it like that, and we can actually evaluate that. But here, we don't actually know. We know that y is a function of x. We just don't know which one it is. So we can just leave it like this. And so we end up with 2y dy dx. So what that means is with the chain rule, when we're doing implicit differentiation, whenever you differentiate the y, we have to keep in mind that we need to use the chain rule. So here, the bottom line is, after all the dust settles, that this is the starting point. D remember dx squared dx is just 2x. And we just got through showing that dy squared or dx is 2y dy dx. So basically, we're just adding them together. Wait, hold on. I think I may have left something out. Hold on a second. Yeah, I think there's a typo here. This should have been, oh Christ. All right, hold on. So I can fix this right now, but I'll tell you what, I'll fix this and post it. It looks like this one is wrong. Looks like the 2y got left out. And so that means what we could do is rewrite this as all right, and so there we go. Okay, so yeah, it was not correct before. It's fine now, but because yeah, right there, I left that out. Okay. Anyway, what about this one? No, leave it there for a second. So anyway, but the bottom line is, so when you differentiate these two, the first one gives us 2x. The second one is 2y, as we just proved, dy dx. And then remember, what we're trying to solve for is dy dx. So that means that we end up with minus x over y. Now, I don't know if Symbolab is capable of doing this. Implicit differentiation. I didn't actually try it. I was afraid what it would do. It's probably capable of this. I just have never seen it done. Let's just try something. Oh my God, it does have it. Oh my God. All right, let's try it. All right, so we had, but I don't know how we were supposed to find that on the actual website. I didn't actually see it anywhere. Well, it's there now, but okay, well, anyway, we're gonna have the original function was x squared plus y squared equals 25. Okay, negative x over y. Yeah, perfect. All right, it's good to know. It's good to have the friend here like this. And in fact, they're trying to be very helpful. Look at this. We're telling you differentiate both sides. So you have 2x, like we saw it, plus 2y dy dx, that equals 0. And then the rest is just algebra. You're just algebraically rearranging it to solve for dy dx. And that's it. But like I said, the challenging part is recognizing that the derivative, or I should say the differential of y with respect to x turns out to be 2y dy dx by the chain rule. If not, if you notice here, if that weren't true, we would have ended up with 2x plus 2y equals 0. We never would have had a solution for our derivative because it would have dropped out of the equation. Okay, so it's because of the chain rule that the dy dx stays in the equation, and then we can solve directly for it. Okay, so now that one is done. So how about this one? Well, we're going to use the same approach. Now, again, you can see, I mean, I guess in principle, you could rearrange this one algebraically too. Like, maybe we should do that just as a double check. I was trying to come up with examples where you couldn't do this, but it's hard to do that. All right, we'll double check that later on. All right, but if we use implicit differentiation, we'll differentiate both sides with respect to x. Okay. The right-hand side was already 0, so its derivative is 0. We split this up into two pieces. This one is easy. This one is just 10. This one requires the product rule. Okay, so that's going to be interesting. The product rule with implicit differentiation. So that is going to be the challenging part. All right. Oh. Okay, so let's see how that would work. Oh, and of course, this implies that d 3x squared y equals d 10x. All right, that's not a problem. But the first term requires the product rule, so we will allow, this will be, and by the way, remember, we're assuming that y is a function of x. It may not appear that way. You see how we've got all functions of x. We're assuming that y is a function of x so that we can let this be g of x, and this can become h of x. Even though it says y, if we're assuming that it's a function of x, we can still use this approach. And but here's the fun part. This will be easy. Based on the power rule. What about y? Oh, it's just dy dx. You can't do anything else with it. So when we apply the product rule, we'll get 3x squared dy dx plus y 6x. That will be this. Okay, in other words, this is telling us that 3x squared dy dx plus y times 6x is 10, because the dy dx of 10x is just 10. And then that means dy dx, 3x squared. I'll subtract that from both sides. And then I'm going to wind up dividing out both sides by this 3x squared. Oh my God, what a mess that was. Um, Actually, no, I think I made a mistake here. Hold on. Let's see. The slides have it. Let's do this with the slides. Hold on. So remember, what would we define here? G of X. We're trying to figure out this differential. This is our G of X. This is our H of X. G prime of X is 6X. H prime of X is dy dx. Fine. All right, so we got that straight. We plug everything into the product rule. Yeah, this is what I had. What happened? 3x squared dy dx plus y 6x. And also don't forget that we also originally were, that was equal to d dx of 10x. Huh. So yeah, obviously I did something wrong algebraically up here. Oh, what did I do? No, I think this is right. All right, I'll tell you what, let's go to Symbolab and see what it says. No, I think this is the part that's not set up correctly, because if you look at it, you can see yeah. Okay, when I did it by hand, this part I was supposed to divide, that's why. Okay, now it works. So I'll post this is obviously I need to make a couple of corrections here. I'll post this version on Blackboard. In fact, I'm going to save it right now with this name. There you go. All right, so the one that says corrected has the right answers, obviously. Okay, so now let's go to Symbolab, which we now know can do this. All right, so what was again 3x squared y minus 10x equals 0. Yeah, 10 minus 6xy over 3x squared. That's right. Okay. No, it was a stupid algebraic mistake. It's so frustrating when you're doing all the complicated things right and then messing up the algebra. So yeah, it's fine now. All right. Anyway. So that one It's important to know that, but again, in certain disciplines, you're not likely to run into these types of functions. What's coming up next, though, is extremely useful in practice. Okay, we're going to start by looking at the derivatives of what are called exponential functions based on this constant e, which we will see later on, formally defined. Well, actually, I might as well show it to you right now. Just a quick preview of what's coming. What you'll see probably at the end of this course or the early in Calc 2 is the formal derivation of E. E didn't just fall out of the sky. It's actually the result of a limit. And we haven't done limits like this one yet. It is the result of a limit. And so far we've avoided doing limits where x approaches infinity, but we will get back to that later on. Okay, so E is a result of one of these limits. Now, what's interesting about E is that it was actually developed in a paper by one of the Bernoulli brothers. There was a family of Swiss mathematicians in, I believe, the 1600s. They were all mathematical geniuses. And what they would do is they would send papers to each other. And sometimes they would send each other joke proofs to see if the others caught on. This is how seriously they took mathematics, where it got to the point where they're pranking each other with phony proofs. So the Bernoullis were very famous. And so the mathematician Euler, you may have heard his name before. In fact, let's grab his biography right now. Yeah, he was a little later, maybe the 1700s. Right. So supposedly what happened was Euler came across one of these papers by the Bernoulli brothers, and he where they invented the concept of E, but they never gave it a name. They just said, here's a constant that could come in handy, and they showed how it was derived, et cetera, et cetera. So Euler apparently was the one who said, it doesn't have a name. Why don't we call it E? E for Euler, because I'm the one who's deciding that it's now supposed to be called E. And so it's stuck ever since. He also is the one who decided to call the square root of -1 I. Okay, so E and I were directly the result of Euler's writings. And so we've been using them ever since. But at least he was the one who dreamed up this idea of negative square root of 1. And so he got to choose the name. But E, he essentially named it after himself, even though he wasn't the one who came up with the idea, because the Bernoullis just never got around to giving it a name. They just said, here's an interesting constant. And that was the end of it. So yeah, the history of math is actually more interesting than you might imagine. A lot of very interesting characters, especially people like Newton. Carl Gauss, who was invented the normal distribution from statistics. He was also kind of secretive and a little crazy, and a lot of strange happenings have happened among these famous mathematicians. But anyway, so that's where E actually comes from. But E shows up a great deal in certain disciplines, in particular finance and economics, because we use it to calculate, let's say, for example, you're putting money in the bank, or you're putting it in the stock market, and your investment grows at a certain rate every year. We can use E to figure out how much money we'll have in the future. So it's very, very helpful in a lot of areas. So exponential functions are the ones that are based on E. And so let's go to Symbolab for a second and just quickly take a look at some of these functions. For example, just E, let's Y equals E to the X. Let's do that one, just to see what it looks like. So this is the simplest possible exponential function. And you can see what's interesting is that it starts out at a very low value in the third quadrant. X is negative, Y is positive, but it's very, very small. It crosses the vertical axis at 0, 1, because e to the 0 power is 1, and then it grows like crazy. Okay, so you may have seen this in high school biology. The growth of bacteria in a colony is often described with an exponential function. It's growing very, very quickly, slowly at first, but then it starts to grow like crazy. And so this type of function is very helpful for describing growth rates, not just for bacteria, but for the value of an investment or the value of a size of a population and that type of thing. So, but of course, as you can imagine, these also have rules for calculating derivatives. And the first one, the standard case, if f of x simply equals e to the x, then believe it or not, the derivative is just e to the x. Okay, you don't see that very often. The derivative is the same as the original function. Okay, but here it is. That is just the way it works. But then if we're looking at some other function, e raised to, let's say, g of x, some other complicated function of x, then we start to need the chain rule. Okay, so once we have something more complicated than this, then the chain rule has to get involved. And so here you can see that if f of x equals e to the g of x power, then the derivative is e to the g of x, but then we need the derivative of g prime of x. Okay, so it's a very simple relationship. But again, because g of x is now more complicated, actually this would work with e to the x anyway. I'll tell you why, because if you treat g of x as just x, g prime of x would be 1 anyway. So technically you are using this rule with the e to the x. It's just that you don't notice it because this g prime of x reduces to 1. And so you end up with f prime of x is e to the x times 1, which is just e to the x. So you can think of this first case as a special case of this one, where g of x is just x. So this is the more general function or approach. This is what we'll be using. So let's look at a few examples. And you can see it's really not a very complicated idea. In fact, it's kind of easy. We like easy derivatives. So we have, if you have e to the 3x, that implies that g of x is 3x, or g prime based on the power rule is just plain 3. And so when you plug these numbers in, you end up with e to the 3x times 3, where 3 is the derivative of this exponent. And of course, by convention, we typically rewrite it like this, right? 3e to the 3x. It looks nicer than e to the 3x times 3. So in general, anytime you have e raised to a power like, let's say, kx, then f prime of x will always simply be ke to the kx power. All right, it's a simple version. It's a simple case to remember. Now, this next one is a little bit trickier, but it's the same idea. Again, we'll need the chain rule. It's just that g of x is a little bit more complicated. And, oh, but also we made it a little more complicated too, because it's 3e to the x squared. So here's the thing. What are we supposed to do with this 3? Oh, boy. All right, well, let's do this. Let's think of this. Let's use the product rule. This is my g of x, and this is my h of x. Now, that's the g of x is easy because g of x is 3, and g prime of x, of course, is just 0. H of x is therefore e to the x squared. The challenge here is what to do about h prime of x. So as we saw before, it'll just be the original function times the derivative of that exponent. Okay, so in other words, because e is raised to the x squared power, by the chain rule, when we differentiate it, we'll have e to the x squared again, but now we're multiplying it by the derivative of that exponent, which is 2x, or some people would say, well, let's rewrite it like this. Not that it matters, but some people are perfectionists. And this is, I guess you can see it does look kind of nice. So then, but we still aren't done because we still have to plug all these results into the product rule formula. All right, so let's do that. Okay, now as it turns out, though, because g prime of x is 0, this will simplify quite a bit. We'll have 3 times 2x e to the x squared plus e to the x squared times 0. So when all the dust settles, we simply end up with 6x e to the x squared. Oh, okay, well, that wasn't so bad. And of course, don't forget, this result right here, this is coming from the chain rule. Okay, that is a consequence of the chain rule. So we involved both the chain rule and the product rule. Okay. Now this next one looks very straightforward, but unfortunately it requires us to use the quotient rule. Now there's nothing wrong with the quotient rule. It's just that it is kind of messy. Okay, but when you see it, you'll say, oh yeah, I see what you mean. This is definitely a case for the quotient rule. So remember, the way it works is that this is g of x and this is h of x. So we have g of x and as we just saw, based on the chain rule, what we end up with is that we still have e to the x squared, but then we have to multiply that by the derivative of that exponent, which becomes 2x. The h of x is just x, which means h prime of x is just 1. And now, of course, we just plug all these in to the quotient rule formula. And if we're lucky, we'll be able to simplify it a little. It isn't really necessary. Okay, so let's see what that turns into. So we plug them in. Actually, you know what I'm going to do? Let me just copy these onto that slide so you can see. Oh boy. All right, hold on. I'll do this. G of x is e to the x squared. G prime of x is 2x e to the x squared. H of x was just plain old x. And h prime of x is 1. So when you plug them in, okay, we have h of x. So here's g prime of x. It's just written slightly differently. And then we have g of x, h prime of x. And then, of course, down here, we simply have h of x squared. Now, at first glance, it looks like, you know, I guess you could theoretically simplify this a little. You could write this. Well, actually, no, you can, because no, you can't. Look at, here's what the problem is. You can factor, but it doesn't really get you anything. All right, so I'll tell you what, why don't we make one up? Because more practice is always good. Okay, so all right, let's see what we can do. Suppose we had this one. Ooh. Now, obviously, we're going to use the product rule. So let's let g of x be 3x squared. H of x will be e to the 2x cubed. And so what you're going to do is figure out g prime of x and h prime of x, and then, of course, plug them in. And see what you get. All right. I think we could use the practice. So I'll give you a minute. I don't know what the answer is either. I just made it up. We'll see how it goes. Actually, I just wrote it slightly differently. Let's use this definition. This is the one we've been using all along. So let me just erase that. Use this one. It's the same thing, but I think it's better to be consistent. So the only really challenging one is the h prime of x, because that involves the chain rule. So the first one is very straightforward. The second one, remember with that chain rule, you've got basically, remember this is defined as e to the g of x. And so all you need now here is the derivative of that exponent, which by the power rule is 6x squared. Okay. And if you choose to, you can rewrite it as 6x squared e to the 2x cubed. It's not necessary. So plugging them in, you get 3x squared. You can see now by writing it like this, that makes it a little easier to simplify it. Then you have e to the 2x cubed times 6x. So when you're done, you can rewrite it as 18x to the 4th, e to the 2x cubed. And then, you can rewrite it like this if you want. And if we can factor, look at that. Okay. So any one of these, the ones in the bottom are fine. You don't have to waste a lot of time simplifying. Well, all right. See if I can think of a really challenging one. Ooh, now we're getting into some deep waters. Um, okay, so let this be g of x. This will be h of x. So the strategy is to figure out g prime of x and h prime of x and then plug them in. Okay, let's see. Um, now we had one just like this, 3e to the x squared. Technically, that one should be done as a product rule. Same thing over here. Let's just analyze this one by itself. If you think of this as g of x and h of x, so using the product rule here on this, it would be 3e to the x squared. Oh my God. Oh, wait, what did I do? What? No, sorry. G prime is not zero. What did I? Oh, okay. I know what I did because I'm thinking of the three. No, I'm doing the wrong thing. Hold on. I just forgot. We're trying to do this one term at a time. All right. So if we just focus on the 3e to the x squared, then g of x is 3. G prime of x is 0. H of x is e to the x squared. 2x e to the x squared is the derivative of h. So this is equal to okay. So this is the derivative of just this piece by itself. What about this mess after this? If you're looking for this 2e to the 3x to the 4th, obviously you're going to take the derivative of each one separately. Let's see, we're going to end up with Wow, I'm sorry that I picked such a messy one. But all right, let's just carry through. So basically, just to recap this, so to apply the product rule here, we just got through showing that g prime of x is 6x e to the x squared, and h prime of x was oh man, no, this is not right. Hold on. All right, let's give that one more shot. All right, so the derivative of this expression right here. That's better. All right, so I'll copy that to the next page. All right, and so now, of course, we can just use the product rule. And let's see, oh, wow, what a mess. So I'll have 3e to the x squared. And then we'll have okay. Yeah, that's what I get for making it too messy. So yeah, on the homework assignment and on the test, I'll try to avoid messes like this. It's because then you're losing sight of the actual techniques. You're too busy with all the algebra. Um, let me make up another one that's a little more down to earth. Okay, now I like that one. That one is not too painful because it's a relatively straightforward product rule. Okay, so clearly g prime of x is 3. Now, what about this? H of x is e to the x to the 4th. H prime of x is that function times the derivative of the exponent. Okay, so now, as far as the product rule is concerned, just copy this back. And when you plug them all in, All right, so simplify just a little bit. 12x to the fourth e to the x to the fourth plus 3x to the, sorry, 3e x to the fourth. Okay, that's much better. That one I like. It's very straightforward. And of course, it illustrates h prime is coming from the chain rule right here. That's what all of this was supposed to be all about, the chain rule for e to the g of x. All right, now, what comes next is we're going to now look at not exponential functions, but logarithmic functions. Most of them will involve the natural log. You're much more likely to run into the natural log than other bases, although we do have rules for the other logs as well. But for the most part, the rules are defined in terms of natural logs. Now, some of these couldn't be any simpler, and some of them are obviously a lot messier. So we also will find that when we're using functions of x, like the log of the function of x, then we'll need to use the chain rule. Okay, so and some of these are a little bit messier than what we're doing with the exponential functions, I would say, but we'll get used to it. We've got several excellent examples here, and we'll get some practice with that. So just run back here real fast. And the whole idea here, this is what you need to know right here from the, as far as the exponential functions go, this right here is the bottom line. If you understand that part, the rest is straightforward because all you're doing is applying other rules like the product rule, the quotient rule. This was the challenging part. This is the new part that we just did tonight for the first time. All right. And we'll have something comparable with the logarithmic functions in a few minutes. Okay. But first, I guess we better knock it off for a bit, and then we'll have our usual break. When we get back, we'll focus our attention on the logarithmic functions. And then if we have a little extra time, we'll at least take a peek at chapter 4, where we're introducing some applications of derivatives, although there's also several new techniques in there as well. It's not just, let's do fun things with the derivatives, but also we learn a lot of new important ideas as well. So, all right, we might as well stop right here since we're pretty much done with the exponential functions. And so now we can go ahead when we get back and just focus on logarithmic functions. All right. All right, we're ready for logs. Okay, so let's start with a simple case. If f of x is the natural log of x, then the first derivative very simply is 1 over x. Okay, that's easy to remember. And of course, now what we're going to do next is we're going to see what happens when f of x is not log of x, but log of g of x. And of course, that means that we now have to bring in the chain rule. But you'll see it's still a very simple calculation because all you have to do is take 1 over g of x instead of 1 over x, and then you'll multiply that by g prime of x, or you often see it rewritten as g prime of x over g of x. So even for the most complicated logarithms, the derivative isn't really that complicated because you're just taking the derivative of g of x, whatever it is, and dividing it by the original function g of x, and that's it. That's all you have to do. So let's look at a few examples. So, for example, here's one. If f of x is log of x cubed plus 3x minus 4, naturally enough, the function inside the parentheses will be our g of x, and based on the power rule, and we'll see that, of course, g prime of x would be, let's just review this really quickly. If you have f of x equals k x to the n, then f prime of x is nk x to the n minus 1. So when you have a polynomial like this, you're actually applying the power rule to each term separately. Actually, let me point it this way. You're doing that to each term separately. So here, for example, in this first case, we'll end up with 3x squared. This one will end up as 3. And here, this is a constant, so it just ends up with a derivative of 0. So therefore, g prime of x is simply 3x squared plus 3. And of course, now all we have to do is put g prime of x in the numerator and g of x in the denominator, and we're all set. And I think it should be clear by looking at this ratio that there's essentially nothing you can do to simplify it. So this is our final answer. So these are pleasantly easy, as you can see, although the e to the x isn't really that complicated either. I just happen to choose some very messy examples of it, but neither one of these is a very complicated rule. Here's one. Now, this one might be a little bit more of a problem, but now here's where you have to sometimes use your cleverness. Often with derivatives, before you just start blindly applying rules, often it pays to look at the function carefully and see if maybe there's something you can do to make it a little bit simpler. Now, if you, like here, for example, if you think of this as log of g of x, this g of x is actually a very messy function. If you were to go ahead and evaluate this, g prime of x would require, the way it's written, both the product rule and the quotient rule, the product rule for the numerator, quotient rule for the entire expression, and you've got a sign in there too. That could get really messy. So what we might want to do instead is take advantage of the properties of logarithms. Okay, and you might recall that the log of x times y equals log x plus log y, and the log of x over y equals the log of x minus the log of y. So why don't we try that? Let's see what happens. So we apply the logarithmic properties. As you can see here, we've got log x squared plus log sine of x minus log of 2x plus 1. And now we can apply this rule very simply. For each term, okay? And so for this one, if you think of this as g of x, g prime of x will simply be 2x. And so that ratio down here will be 2x over x squared. Remember, it's always g prime of x over g of x. For this one, remember that the derivative of the sine of x is simply the cosine of x. And so this ratio, g prime of x over g of x, gives me cosine of x over sine of x. And then here, if this is g of x, g prime of x is just 2. 2 over 2x minus plus 1. Now, of course, if you want to simplify it a little, you can do so. Like, for example, this could be rewritten as 2 over x. This is actually the cotangent of x. This one can't be simplified, but the way it's written now, it's fine. Okay. So you can see, though, rather than running off and trying to do take this pretty messy g of x, x squared sine x over 2x plus 1, we could have done it, but it would have probably taken a lot longer. This way, you can just break it up into 3 manageable pieces, and then you can apply the rule, f of x equals log g of x. The derivative is simply g prime of x over x. Now, in the next case, we'll have another case where we can use the properties of logarithms to make our lives a lot easier. That's always nice. You might recall that if f of x is something like this, this is the same thing as n log x. Okay. And so we'll use that same idea here and simplify this as 5 log 3x plus 2. Now we're good because here we just simply have a constant, and then we can apply the rule we had before. The derivative of log of g of x could be simplified, used very simply right here. So if we think of this as our g of x, by the way, we can just keep the 5 out here. We don't really need to use the product rule here because the 5 is a constant. It'll just multiply by whatever derivative we get here. So g prime of x is simply 3. So the derivative of just log 3x plus 2 is going to be 3 over 3x plus 2, or we can simplify that as 15 over 3x plus 2. So that turned out rather well. I think you'll agree. It could have been a disaster, but instead we were able to simplify it and we end up with something nice. All right, now, what about the other bases? So far, we've spent all of our time on natural log. And again, this is something you'll see very frequently, but sometimes we might run into logs that are not base E. What do we do then? Do the rules apply? Yes, but they're a little different. Okay, so here's the first one. Imagine we have f of x is not the natural log of x, but the log to base b of x. In the first derivative, instead of simply being, just remind you that here, the first derivative is 1 over x. Here, it's similar looking, but instead of 1 over x, we need this. The log of this base b. Okay, so this is the adjustment we have to make when we're using a base other than natural log. In other words, if this was e, if b was equal to e, then we would just end up with log x, and we don't have to worry about this. And especially because the natural log of e is just 1 anyway. What about then this case? Oh boy, what do we do now? Well, once again, it's very similar to the rule for the natural log. In other words, Okay, so now we replace natural log with log base b. And so these are the same, except, oh yeah, here we go. Once again, we need that log b in the denominator, natural log b, that is, to make it work. All right, so, maybe we'll make up an example here. Oh, first, let me just leave it here a little bit longer so you can see it. But so I'll just make up an example. And then I guess we can confirm it with Symbolab. All right, so let's try this one. Okay, so if in practice, if you're using a log that is not base E, chances are pretty good it'll be base 10, or if not 10, possibly 2. You do run into that sometimes, especially in disciplines like computer science. So here you would have g of x and g prime of x based on the power rule is going to be 6x squared plus 4. So therefore, you'll have 6x squared plus 4 all divided by 2x cubed plus 4x times the natural log of 10. That's it, and you're done. So let me see how let's go get Symbolab. Let me put it back for a second, just in case you weren't done. So again, it's the same principle as what we had before when we were using natural logs. The only change is the natural log ln b in the denominator. All right. So let's see. So we're looking for the derivative of log of 10 2x cubed plus 4x. So it's got 3x squared plus 2. Oops. Oh, you know what they've done? Hold on 1 second. Looks like they simplified it, which I did not do. You see what I mean? You got 3x squared plus 2. So in other words, let's go back to this for a second. You can see we can divide the numerator and the denominator by 2. Okay, so let's get back to it. Now let's make sure that they're the same. 3x squared plus 2 over x cubed plus 2x. Oh, something's not right. Oh, no, because they factored out an x. I didn't even see that. All right. I don't know why they did that, but so they should be the same now. So the denominator is x squared plus 2. Times log 10. Yeah, that's it. We're good. All right, that was a good example. All right, now, here's an interesting result. What if you had something like this? What if your function is some constant raised to the x power? B is just some constant. Then the derivative is that function times the natural log of b. So if you had something like this, then the derivative would be 5 to the x times natural log of 5. Okay, so that's very straightforward. Now, of course, you can imagine what's coming next. What about this case? What do we do now? Okay, well, it's only slightly more complicated, but of course, as you can probably guess, it involves the derivative of g of x. Due to the chain rule, we have to incorporate the derivative of g of x. So how does that work? Well, the only change is, as we expected, g prime of x. So remember before, we had this. And so what's different now is this piece. And you can think of it as actually having it there, but just be aware that what you've actually got here is g prime of x would be 1. So technically they are the same rule. It's just that here the derivative of x is 1. So we just drop it out. All right, let's try this. So I'm going to put a little reminder up here what the rule is. Well, actually, no, we don't need that one. Sorry, I copied the wrong one. Oh, I forgot. It always does that. Whenever you change the font, it's something, it somehow messes up the exponents. All right, there we go. So based on that rule, oh, God, I copied the, wait a minute. This is the wrong rule. Anyway, hold on. I did it again. Log b of x. Let me go get that one. Here we go. This is what we were after. So if f of x is log b of x, then the derivative is 1 over x log b. So here b is 3. So we just end up with 1 over x log 3. Very good. So the next one will have, it'll be a log not of just x, but g of x. So let me go grab the rule. Okay, so f of x is log. Oops, no, that's not the right one. That was meant for natural log. Sorry. Let me go grab it, the right one. This one. Yes, here we go. Yep, now we're good. Okay, so it's log, not natural log base b of g of x. So this is our g of x. This is our base. Okay, so base is 5. G of x is 2x to the fourth minus 3x squared. Based on the power rule, g prime of x must be 8x cubed minus 3x. So we can just use this rule right here. We'll have 8x cubed minus 6x over 2x to the fourth minus 3x squared. And then don't forget, we also have the natural log of 5. Now you can see, you can clearly cancel out some of these x's. You can simplify it a little. But I think that's all. Yeah, that should do it. All right, now we're going to do a couple of examples where we have a constant base and the exponent is either x or a function of x. Okay, so let me go grab some rules here. Okay, so we have b to the x, b is 3. So according to the rule, the derivative is just the original function times the natural log of the base. And that's it, you're done. Okay, but what about when the exponent is g of x? All right, here we go. So we have f of x, b to the g of x. So this is g of x right here, which according to the power rule means that g prime of x is 6x, b is of course 3. And so when you plug these in, right here we have b raised to the g of x, the original function. G prime of x is here. And then finally, this is log b. I don't know if there's really, I mean, you could simplify it a little, I suppose. Not much though. You could rewrite this as 18. No, you can't. Sorry. No, what am I doing? No, because this is 3 to the 2x cubed. This is 6. No. So we have to leave it alone. It's fine the way it is. All right. So that takes care of derivatives of logarithmic functions and exponentials. So that was the end of this appendix. So now we can, like I said before, just at least take a peek at chapter 4. So this is meant to be like applications of derivatives, but they're actually introducing more new concepts anyway, in spite of the way it sounds. It's not just, let's just do some real world examples. There are many new concepts in this chapter, especially when we start looking at optimization. There's also a discussion about how to handle more advanced limits. It turns out that when limits get very messy because we're converging to zero or infinity, we can often speed things up a little by taking the derivatives of the numerator and the denominator of our expression. And so we'll see that later on in this chapter 4. But right now, we're going to start by looking at and there's a lot of topics, as you can see, something called linear approximations. So what is this all about? Well, let me just show you a little graph. Suppose you've got some kind of a function here. And this could be almost anything. Let's say it represents profits. Y is profits. And X is units sold. And so let's just say that at the moment we are right here. Well, what we're trying to do here is say this. Imagine that if we sell 100 units, our profits are $2,000. Now, what we might want to know is, well, what happens if I increase my output to 101 units or 102? What's going to happen to my profits? So what we can do here is use this tangent line to give us at least an approximation of what will be the impact on Y of a change in X. So in other words, if X increases. Now, by the way, this picture, I mean, it may not be the best drawing of this, but the idea here is that you can use a tangent line to give an approximation of how much this function changes when X changes. So if X increases to 101, we can use the tangent line to approximate at least the change in Y. In other words, we want to know, listen, if we just produce one more unit of our output, what is the likely impact on our profits? What we can do is come up with a rough idea just by taking the slope of this tangent line. And we'll see that as long as the change in X is not too large, we should get at least a reasonably good approximation to the change in Y. For certain cases, this will work better than for others. And this is actually very useful in practice because it means that we may not necessarily need to have an extremely detailed understanding of this profit function. As long as we have a rough idea of what's happening at each output, we can use this type of approach to help us understand what will happen if we increase the amount that we're producing. So now the problem, though, in fact, let me draw another picture here, is that, like I said, this only really can work if the change in X is very small, because here's what's happening. And of course, this depends on the function. From here, I'm using a straight line to approximate the behavior of this function, which is clearly not a linear function. So if I move from, let's say, here to here, x1 to x2, the impact on Y, I should pretty much capture the impact on Y without too much difficulty. But if I move all the way up to x3, you can see that the actual function's value is way above what the tangent line would suggest. So in other words, here, the approximation is very poor, or I'll call it inaccurate. Whereas between these two, you can see, you can't even see the difference between the tangent line and the function. The approximation here is highly accurate. So it's understood that when we use these methods, they're only accurate for relatively small changes in X. But having said that, they can do a very good job. So anyway, so what we're going to do is start with this equation. And it turns out that no matter where we're looking on the curve, if this is point A, this would be, of course, f of A. The equation of the tangent line can actually be written with this formula. It's written this way for a reason. Well, you'll see as we go along, it's more convenient to express it this way. But this actually is the equation of that tangent line at point A. Okay, so we're going to look at a couple of examples of this. So let's say we're looking at 1 over x. Now, I did go look up the graph in Symbolab. So here's our, remember we saw this earlier on, we have a vertical asymptote. So the function is discontinuous. In fact, we have two asymptotes, the horizontal and the vertical axes. So imagine ourselves wanting to know the tangent of this line at a given point. First things first, we'll need to know the derivative of this function. So here's the key to this whole thing. 1 over x, remember, is equal to x to the minus 1 power. So that means that if you think of this as kx to the n power, k is 1. There's an implied 1 here. N is negative 1. So when you take the derivative, you're going to end up with negative 1, 1, x to the minus 1, minus 1. Which is saying the same thing as negative 1 over x squared. Okay, so we're going to need that for our formulas. For calculating the tangent, we're going to need to know the slope of the function at any point. All right, so imagine we pick 2. We're interested in 2, the behavior of the function when x equals 2. Well, you can plainly see the slope is negative. Okay. The question is, what exactly is the equation of that line? All right, well, let me just remind you what this equation looks like. This is what we're aiming for. So if we're looking for x equals 2, a is 2. Since the derivative of x is 1 over x, negative 1 over x squared, f prime of a, or 2, is negative 1 over 2 squared, negative a quarter. Good. Okay. Now, we also eventually will need f of a. Remember, f of x is 1 over x, therefore f of 2, let's change that to f of 2, is equal to 1 over 2. Fine. All right. So now we got all this information. Let's put it all together. This is the equation we're aiming for. We already know that f of x is 1 over x. F prime of 2, remember, we're assuming that a is 2. F of 2 is a half, f prime of 2 is negative a quarter. So when you plug everything in, you've got 1/2, negative a quarter, x minus 2. Okay. Now, if you want to, you can rewrite that in the traditional form for a straight line, y equals mx plus b. I've done that on the next page. So that's what we found. And when you do the algebra, you'll find that this is the actual equation of that line. But it turns out that for what we're doing in this section, this is really the more convenient format. Okay, so you can leave it like that. If you really want to know the equation of the line, you can rearrange it. But for coming up with the approximations of the small changes that we need, this format is probably easier. And we'll see when we do some examples. All right, then. So let's go back to the graph and see real fast. So we're saying that the intercept should be 1 and the slope is -1/4. Well, I don't know. I didn't do such a hot job there, I guess. You can see it. No, actually, no, I shouldn't say that. I think now that I'm looking at it, 1 is right about here somewhere. So, okay, it's fine. It's not that bad. And again, we could use that information to figure out, for example, approximately what would be the value of this function at a point very close to 2, like 2.1 or 2.01 or something like that. Okay, so like what if we wanted to know f of 2.1? Well, using this technique, here's what we're going to do. So this is, remember, this is the equation we came up with. This is, remember I said this format will be a little bit more convenient. So we'll stick with that one. And what we're going to do is replace the x with 2.1 because we're trying to solve specifically for 2.1. And so that's going to give me approximately 0.475. Okay, so on that curve, when x is 2, the function is supposed to be approximately actually it should be 2.1, 0.475. Now, in this case, since we actually know the functions, the functional form, we can actually figure out what the correct value is by just plugging it in. Now, you might say, well, why don't we just do that in the first place? Well, it turns out in practice, we may have scenarios where we have a lot of information about a function, but we don't know the actual equation of the function. And so this is a good way to come up with the results that we need. So this is definitely, it may not seem like it right now, but this is going to be very helpful in cases where we may not have perfect information about the function itself, but we can still use this to come up with approximate results. So it turns out that f of 2.1, plugging that into the original function gives us about 0.47619. So it was pretty close. The approximation error wasn't too bad. Let's see if I can draw it. So let's just say this is 2, and let's say this is 2.1. Yeah, it's really hard to draw with so little space here. Well, you can see there is a small gap between the actual value, which is this. You know what? Let me see if I can make that bigger. So I'm going to exaggerate it just a little bit so you can see it better. This is 2.1. So we just got through seeing that the tangent gives us an approximation of 0.475. The actual value was something like 0.476. So you can see the approximation isn't too bad. But if we tried to use, let's say, whatever this value is here, you can see the spread between them is getting quite large. Let's say this is 5. So if you try to go all the way up to 5, you can see that the approximation will not be very good. All right. So anyway, so the formula then that we just used gets a special name. It's written in this book as L of x. It's called the linearization of f of x near a. In other words, it's a linear approximation to the function at point A. Okay, and so we'll be using this for its own sake, but also in the next section, when we introduce the concept of differentials, we'll be able to see how this helps us understand what this notation actually means. Because dy dx itself has its own unique interpretation. The dy and the dx are actually just very, very small changes, and they tie in directly with this equation. Okay, so in other words, this gets back to the idea of what exactly is a derivative. So we're building up to something very important here, which we'll see, but not just right now. Let's see. All right. Well, all right. Now, by the way, in the book, I copied this out of the book because for the next example that's coming up, they're giving us a very nice graph. So you can see how for the function square root of x, you can use the tangent line to approximate what will happen if we move away from x equals 9. You can see the approximation will actually work pretty well for quite a while because this portion of the curve is actually pretty close to being linear. So some functions lend themselves better to this type of thing than others. Some functions, it won't be very close at all, except like right in that immediate vicinity. But for some, like this one, you can see the approximation can actually work quite well over a wide range of x's. Okay, so all right, well, this is a fairly messy example, so maybe we'll save this one. But anyway, yes, as I mentioned, there's a lot of key topics in this chapter. This is going to be one of the big ones. Like I said, maxima and minima, this is where we get involved with optimization, limits at infinity, and we're going to formally study asymptotes, optimization, L'Hopital's rules, where we get to expand our understanding of limits. Newton's method, and that is the same Newton, is used to help us find the solution to an equation that doesn't have an explicit solution. We'll see what that means when we get to that point. And then we're going to understand there's, we've been focusing a lot of attention on taking derivatives. There's actually a reverse process that we can apply, which is called antiderivatives. Okay, it's kind of like, I guess, matter and antimatter, but no, maybe not. But yes, so we're going to cover a lot of heavy duty topics in this chapter 4. So, but again, a lot of these are meant to be used for practical, useful purposes. We're trying to make maybe not be quite so theoretical and be more useful, especially the optimization material. But there's a lot of important and very interesting topics in this chapter. So we've got a lot to look forward to. So anyway, but since it's so late, I guess we better cut it off here. And I'll see you all on Thursday. All right.
Thanks, Professor. Have a good night.
See you later.
Thank you.